Hello class, it's just me, Wee again, or Mr. Wee again, I'm sorry. I just want to kind of give you, just from the first part, I just want to give you maybe 2 examples. Maybe you can try on your own that we just talked about for L'Hopital's rule. So one would be if you took the limit of x approaches infinity of x squared plus x over e to the x to the third power. That one's a little bit tricky. Okay, this will involve chain rule, right? The chain rule. And then also another one that you could try would be the limit as x approaches 0 of 1 plus sine x over cosine of x. Okay, so this should be solvable using L'Hopital's rule, but it's a good exercise to kind of do. So what I would suggest, maybe, I think I'm going to have a lot of parts up, hopefully, by the time you're watching this in class. So it's up to you at this point if you want to pause this and you want to try this out. So why don't you, sorry, substitute teacher, but the students, why don't you guys just decide whether you guys want to do this on the whiteboard for like the next 5 or 10 minutes. We have a lot of content to cover, or you can go ahead and fast forward, and then I'll show you just like because in the next few seconds I'm just going to put up the solutions for this and just briefly explain what's going on. But otherwise, yeah, you could try this out for the next 10 minutes, but we do have a lot of content to cover. So why don't you pause the video right now, talk really quick about whether you want to do this or not, and then if you do, just continue on and work on the whiteboard, and then unpause this video and I'll show you the solution. Okay? Alright, so pause the video. Hopefully you've unpaused it by now, so I'm going to show you the solution. So it's the exact same 2 problems now with the solution. So here, what you're going to find out is if you actually input infinity as x approaches infinity for this limit, it'd be like infinity squared plus infinity times over e to the infinity squared, base e to the infinity power cubed. I'm sorry about that. And you can kind of debate about, oh, maybe the bottom is going faster at a faster rate because it's exponential, but the fact is you have some form of infinity divided by some form of infinity. And even though it has a check mark, what that says is what I wrote as an original note for myself is this definitely means that this is indeterminate and you have to do L'Hopital's rule. So the next step is to actually take the derivative of the top and the bottom, and then you should get 2x plus 1, which will give you 3x squared times e to the x cubed. So essentially the derivative e to the x cubed is just itself, but because the top exponent has a part that you could also differentiate and take the derivative, you're going to do the chain rule. So the derivative e to the x cubed is e to the x cubed times whatever the derivative x cubed was, which is 3x squared. So that's why that comes down at the bottom here. Okay, and you can kind of get a sneak peek already. If you plug in infinity, you're still going to have 2 times infinity plus 1 over 3 times infinity squared times e to the infinity cubed. If I plugged in infinity, which would still give me some kind of form of infinity divided by some kind of form of infinity. I did another check. Basically, that should be an x, saying like, yeah, that's not good. You got indeterminate forms here and here, so that means we got to take the L'Hopital's rule again for this example. Now, that means you have to take the derivative of the top part and the derivative of the bottom part. The top part's not that bad. The derivative would just be 2. The derivative of 2x plus 1 would just be 2 plus 0, right? So that's not a problem. You got 2. The bottom part, be very careful. You can look at this as 2 different parts that are being multiplied together, 3x squared times e to the x cubed. So hopefully you guys maybe try this, or at least if you guys can see now, there'd be a struggle to figure out how to do this. What you're supposed to do is you're supposed to do the product rule. I know it sounds awful, but what that means is you're going to take the derivative, like it'd be like u v prime means you take so you would assign u and v to one or the other terms that are kind of separate that you could take the derivative of. So you take uv prime plus vu prime. Okay, so what you're going to end up getting is, like in this case, 3x squared. I took the derivative of u, I guess, in this case. So it doesn't really matter what order you do it in, as long as you take the product of one guy, like u, let's say, and then you have to take the derivative of the other, and then you have to multiply u times v prime, plus you take just the base component or the base part of the expression here, and you multiply it to the other guy, but now you take the derivative of the other guy. So it's time plus vu squared. So in this case, it really doesn't matter. I kind of went out of order. This is technically vu prime, but it's 6x times e to the x cubed. And over here, I did, let's see, 3x squared, or what did I do here? Did I do something correct? Did I do something incorrect here? Oh, okay. This one seems a little bit confusing. It's 3x squared squared times e to the x to the third power. What I did was, this is technically, if you had to look at this is technically uv prime right here. This is uv prime. It's just hard to see because you keep the u the same, which is 3x squared. Alright, never mind that squared. And then when you take the derivative e to the x cubed, it's going to be e to the x cubed. It's going to be e to the x cubed, but it's going to be e to the x cubed times 3x squared again. So just to kind of write this off on the side, if you don't understand what I just did, v prime is going to be ex cubed, right? The derivative of ex cubed is just ex cubed, but don't forget the chain rule up here. I bring this down, it's going to be 3x cubed, or 3x squared, right? But keep in mind that when you're doing u times v prime, okay, u is actually 3x squared. So it's 3x squared times v prime, which is this whole thing. It's e to the x cubed times 3x squared. And then what you're going to end up having is e to the, I'm sorry, so it's kind of hard to see, I guess. But you're going to end up getting e to the x cubed times 3x squared times 3x squared, which is shorthand would be e to the x to the third power with 3x squared squared, okay, because 3x squared occurs twice. So I know that's very, very confusing. So just for some kind of clarification. And basically, essentially, if you plug in infinity, I really don't need to go through really intricate math to be like, what is 6 times infinity times e to the infinity cube plus... Basically, once you find an x on the bottom and then you plug infinity, it's just going to be some form of infinity. And the great thing is, what we try to do is we try to get to a point where either the top or the bottom was going to have a whole number, and the bottom or the top was just going to have infinity. It was something over infinity, or infinity divided by something else. In this case, we got 2 divided by infinity. And considering that infinity is conceptually the biggest number you can, or the biggest value you could possibly have, it's not a singular value, it's just a huge value. 2 divided by a huge value is just going to be essentially approaching 0. The limit is approaching 0, okay? So remember, the limit's not actually like what the actual value is of the function, but what it's eventually approaching. It's approaching 0, pretty much, okay? So over here, this is actually pretty nice. I just took the derivative, both the top and the bottom, and you only really need to do it once, because if you plug in 0 right now, you're going to get indeterminate form, I believe. So it's 1 plus, let's see, oh, actually, funny enough, I actually wrote a note to myself. Yeah, you could do L'Hopital's rule here, in which you do the derivative of the top and the derivative of the bottom. It's so funny because I just made this mistake, and you get cosine or x over negative sine of x squared, which is, and then if you put in 0 here and here, you're going to get 1 divided by negative 0, technically, because that's negative in the front, remember? And the derivative of cosine is negative sine x, which would give you negative infinity. But the truth is, which works, by the way. This isn't infinity divided by 0. This isn't infinity divided by infinity. This is not indeterminate. But if you actually go back, did you need to actually do this? Did we even check, or did I even check to see if we needed to do L'Hopital's rule? And the truth is, I didn't. But if you just go back and plug in 0, you're going to be fine. I believe 1 plus sine x, or 1 plus the sine of 0 is just 0, I believe. And then cosine of 0, I believe, is 1. So let's say it'd be 1 plus 0. So actually, 1 plus 0, basically the sine of 0 would be 0 over cosine of 0, which is just 1. Oh, actually, I'm sorry, yeah. Mr. Wee's really goofing up here. Basically, this will give you the correct limit of 1, and this over here will give you an incorrect limit because you did not need to apply L'Hopital's rule at all. Let me check my work here. 1 plus the sine of 0, yes, is 1 plus 0, and then the cosine of 0 is 1. So yeah, it should be 1, yeah. Please tell me if I made a mistake here, because I'm just doing some quick trig right now, and I feel like I'm brain farting right now. But essentially, always check. The main the main lesson I'm trying to teach you right now is that if you don't need to apply L'Hopital's rule, don't do it. Okay, so always check. If you just plug in 0, it should be fine. Okay, so this took a little bit longer than I anticipated, so this is going to be part 2. Okay, and then the next one we're going to start on what's called indeterminate products of 0 times infinity. Okay, and then I'm going to show you what that means in just a second. Okay, guys, I'll see you guys in a bit. So go ahead and take a breather, and we're going to stop, and then we're going to go on to part 3 whenever you're ready. Okay, thank you guys so much. Bye.